All right, so for the next segment, we're going to dig a little deeper. We're going to, here, let me share the tablet here. We're going to work to understand how the anomalous transition metals are incorporated into the Aufbau principle. What are the differences in the electron configuration there? And we're also going to understand better how to count valence electrons. Those are the electrons that are going to be available for interactions and for chemical bonding, as we're going to see soon in the upcoming chapters. Okay. So let's do a little review first. Let's identify the atom with the following ground state electron configuration. So I'll pause for a second, or you pause for a second, think about this, and then we'll come back. Okay, so argon has 18 electrons. We should remember those noble gas electron configurations because they'll be very useful in interpreting the condensed electronic configuration. So 18 electrons, and how many more does it have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So right off, we know we're looking for something with 28 electrons. And if it's a ground state electron configuration of an element, that leads us to nickel. That has 28 electrons. And specifically, if we're to look at the electron configuration there, it would be argon, and then 4s2, and then there's 8d electrons, so 3d8. So that would be the electron configuration of nickel. It has the 4s subshell completely filled, and then 8 of the 10 slots in the 3d subshell filled. Okay, good. So moving on there, but the transition metal, that was a transition metal that did obey all the rules. There's some anomalous electron configurations in the transition metals. So let's take a look at chromium. We'd expect, just by general principles, that when we get to 6 electrons, we would have a 4s2, 3d4 if we had 6 more electrons than argon. But when it turns out that the actual configuration is 4s1, 3d5, that when we go up from 4s2, 3d3, the next electron, actually you get 2 electrons added to the d and 1 coming up from the 4s. So why is that the case? Well, in this case, we're actually filling 2 half subshells. If you go through all the work to solve Schrödinger's equation for a multi-electron system, it turns out there's particular stability into having half-filled subshells. It's not immediately obvious why. All of these energy levels are very close together, but that ends up being the more stable configuration once you have 6 electrons past argon, 6 protons and 6 electrons past argon. Another example would be copper. Here for copper, you'd expect it, given that it has 11 electrons and 11 protons more than argon, to be 4s2, 3d9 if you're just filling them up in order. But actually, it turns out to be 4s1, 3d10. Here, you are filling 1 half subshell and 1 full subshell. Again, all of these energy levels are very close together, but this is what you'd expect. Okay. So here are all of the electron configurations that, for the entire periodic table, and they're the ones I've indicated in red or anomalous. They occur because of closeness in the energy of 3d4s, 45s, 5d6s, 6d7s. And if you look, a lot of them right here have that pattern where you have only 1 s electron and a full d subshell. Several others have the pattern of of a half full S subshell and a half full D subshell. And then there's a few others that are just weird. Again, all of these energy levels are so close together that it's not entirely surprising that as we shift the exact number of protons and electrons around, we get weird behavior there. Down here with the lanthanides and actinides and the F block, there's a lot of weird orderings here. Don't bother about those. You should know that frequently the electron configurations down here, because the 4F is sort of wedged in between the 6S and the 5D, and so there's a lot of weirdness going on. And so I think the thing to remember is, especially we're going to be doing exams in this class open book, is when you write out an electron configuration, think, is this one of the ones, might this be in the range that might be anomalous? If so, I'm going to look it up and check. So I think that's the thing to be aware of. It's not always the same. It doesn't matter. Yeah, there are some things like whether something is magnetic or paramagnetic or diamagnetic will depend on the number of unpaired electrons. So just always remember, especially with the transition metals, especially the ones where you have the chance to fill half subshells or full subshells, that there might be some exceptions in building up the energy levels from just strictly 4s, 5d, 4p.